people, buckle up.
It's gonna get mathy.
Yeah, today's gonna be the most mathematically heavy my videos have ever been, except for the first time I did HLM videos. So you remember this formula? Depression is equal to B0 plus B1 times stress plus E. Well, I kinda lied to you when I showed you that. Because really it ain't that simple. It's actually depression subscript I is equal to B0 plus B1 times stress sub I plus E sub I. What does that I represent? That represents the ith individual. So if you are the 99th person in your data set, your I would be 99. So depression subscript 99. I know that's a little complicated and convoluted. Why do mathematicians have to make things so hard? I don't know, and we statisticians like to follow in their lead. There's something about making something complicated that makes some people feel better about themselves.
I know something nobody else knows. I'm amazing.
Loser. All right, so let's look at a data set and see how this might work. So here we've got person and then their index or their I, their depression and their stress. So depression subscript 3 represents depression for the third person, which is Andy. Poor Andy, he's got an 18.8 depression score. Next time you see Andy, give him a big hug and tell him you love him. Andy's having a rough time. And if we were to write the equation out using subscript notation, we would say depression subscript 3 is equal to B0 plus B1 times stress sub 3 plus E sub 3. And for Andy, that would be 18.8 is equal to B0 plus B1 times 7.7 because that is Andy's stress score plus E sub 3. And I was too lazy to figure out what B0 and B1 are. And if we knew those, we would know what the error was, but you get the idea. So implicit in all the regression that we were doing or all the linear models we were doing, we had that subscript. I just didn't talk about it because it wasn't important. Well, it's kind of important now. Because with HLM, we need those subscripts and they make things a little bit more complicated. But they're not that much more complicated, I hope. Because now, not only do we have I individuals, we also have J clusters or J groups. So if we have 5 therapists, there's going to be J is equal to 1, 2, 3, 4, and 5. So our new outcome variable is going to be depression subscript IJ, which is the depression of person I within the cluster J. And so when we do that, that allows us to model different slopes and intercepts for each and every group. So let's look at an example. So we have depression IJ is equal to B0J plus B1J times stress I plus EIJ. Are you kidding me?
I swear, statistics will be the death of me.
Math is scary!
And I get it, I know, this is really weird and really funky, but kinda has to be that way. So we have the B0J, what does that mean? Well, B0 in regression means intercept, and the J basically means there is a separate intercept for every J, or for every cluster. And so if we were to break that down even further, we could even write an equation for B0J. So B0J is equal to gamma 00 plus U0J. Gamma, we're using gamma now?
Oh boy, headache's coming on.
It's all Greek to me, and that's okay. Yeah, I don't know why statisticians decided to make things complicated, but they did. In this case, gamma 00 means the grand intercept. It is so grand it would wear a top hat to a party.
Oh, please stop.
Or the average intercept across all groups. Remember I lied to you earlier and I said it was a little more complicated than that and that we don't have fixed effects if we have a fixed slope? Well, actually we do have fixed effects even when we have random effects. And so that's what gamma 00 is. It is the fixed effect of the slope, or it is the fixed slope. So again, let me say that again. Gamma 00 represents the fixed, I said slope for all that. Now I'm gonna have to say it all over again. Gamma 00 is the fixed intercept, meaning that when you estimate every single person's equation, every one of them will have a gamma 00 in their equation. So gamma 00 is the fixed intercept, or it is the average intercept across all groups. And what is U0J? U0J is nothing more than the deviation of the jth group from the fixed intercept. So let's put this in practical terms. Let's say the fixed intercept is 10, but this particular therapist within his group, his intercept is 11. So what is his U0J? It's plus 1. Because again, 0J represents the deviation of a cluster from the fixed effect. So that's how you would handle the intercept. Now let's look at the slope. Again, before we had a B1J, and now if we were to break that down, we would have B1J is equal to gamma 10 plus U1J. So why is it 1, 0 and the intercept is 0, 0? The first subscript refers to what parameter it is. So you remember when we did basic regression, we had a B0 plus B1. B0 is always the intercept. And so gamma 0, 0 represents the 0th parameter in the model, which is the intercept. And the second subscript is always going to be 0 for the fixed parameters, just to indicate that these are the fixed parameters. Just like before, we have a U, but this time instead of 0j, it's 1j, because again, it's referring to the slope. Let's say that that intercept is 10, and let's say that that intercept there for that group is 11. Then gamma 0, 0 is going to be 10, and gamma 0j for this particular group is going to be plus 1. And let's say this slope here is going to be 0.5, and this group has a weaker slope, so it's going to be a negative number, and let's say that its slope, instead of being 0.5, is 0.25, so its value of U1j is going to be negative 0.25. I know that's complicated, and I know it's tricky to think about the notation, but as Richard Feynman said, nobody understands math, people just get used to it. So just get used to it, spend some time looking over it, watch this video over and over again, inflate my view counts as you wish, and it'll come to you. So taken together, if we look at this equation all together, we would say that depression is a function of a few things. One, it's a function of an intercept that differs between therapists, meaning that there is a different intercept for each and every therapist. And we also have a slope, and that slope has a fixed effect that is common among all therapists, but there's also a different slope for each and every therapist. And then finally we get to the EIJ. That basically says every individual, that's where the I comes from, has their own residual, and they belong to a particular group. And here's a handy little visual that shows gamma 0, 0 is the grand intercept, and then U0j, that is therapist J's deviation from the grand intercept. And then we have gamma 1, 0, which is the grand slope or the fixed effect slope. And then we have U1j, which is therapist J's deviation from that grand slope.
Isn't it lovely?
So let's go ahead and look at an example. So here we have an alcohol use data set. This is a real data set, and we are looking at alcohol consumption among youth. So we have an ID variable indicating which person it is. That is our cluster indicator. And we have an age variable, 14, 15, and 16, indicating the age at which we ask them these questions. COA is child of alcoholic. Male is whether they are a male. 0 means they are female. 1 means they are a male. And then age underscore 14 represents the number of years since they were 14, which is redundant with the age variable, but you get the idea. And then we have alc use or alcohol use, which I believe represents the average number of drinks a week. And then we have peer, which is the average number of alcoholic drinks your peers consume. And then we have two other variables. C stands for centered, and we're not going to get into centering in these videos. And once again, we have an ID. Notice that it is repeated. If you have an ID that is repeated, that's a good indication that you should probably do mixed models. And notice also that the only things that change from time 1 to time 2 to time 3 within an individual are age and the number of drinks they consume. By the way, you can only model something as a random effect if it varies within a cluster. If every score within a cluster are the same, you can't model it as a random effect. And so we might ask a question, and that question is, to what degree does alcohol consumption increase as a function of age? You might also ask, of all the predictors we have, which is the best predictor of how much these youth will drink? Could it be peer influence? Could it be their age? Or could it be the fact that they were or weren't a child of an alcoholic? These questions we can ask using hierarchical linear models. So I'm going to show you some R code. This isn't my R code video. I'm going to go more into details in the next video, but I'm going to show you some R code just to give you some exposure. The first model we're going to fit is a random effects ANOVA. That's always a good starting point, and you'll learn why in a future video. And in this model, we don't use any predictors. We just fit a fixed effect mean and see how much these groups differ on their, in this case, average alcohol consumption. If we were to look at this in mathematical notation, it would look like this. Alcohol use Ij is equal to B0j plus Eij. Again, there are no predictors here. And if we were to expand B0j, we would have gamma 0, 0, which again is the fixed intercept, plus U0j. And of course we could put all these together and just replace B0j with the full equation, and you would get something like this. Alc use Ij is equal to gamma 0, 0 plus Uij plus Eij. Wow, that is so much fun to say. Next time someone challenges you to a tongue twister, challenge them to say alk use ij is equal to gamma 00 plus uij plus stress ij plus eij. Nailed it. Unfortunately, all the tools within FlexPlot we've been using so far, we can use here too. So here's some R code that loads the dataset alk use, which is a part of the FlexPlot package. Here's the R code we would use to fit a random effects model. Notice there are no predictors, but we do have to have a 1 in there. And 1 is the way that we tell R that we're fitting an intercept. So on the left side of the parentheses are the fixed effects, on the right side are the random effects. So we are telling R that we want a fixed effect, or gamma 00, and we are also telling it that every ID is allowed to have its different mean. So this 1 refers to gamma 00, and then this one right here refers to uij. And taken together, those become our B0J. The lovely thing about FlexPlot is we can visualize this. So if we type in visualize mod and then plot equals model, then we get something that looks like this. And we see that very clearly that the average alcohol use differs within cluster. And we could even look at the results of what R gives us. And I don't actually spend much time looking at this because I got some functions in FlexPlot that make it easier to conceptualize what's going on. But for your information, this right here, the 0.5731, that represents the variance, or it's the variance of each person's mean from the fixed effect mean. And this right here, the 0.5617, that is the variance of each individual from their mean. Maybe it's best to understand this visually. This 0.5731, that represents the deviation of each group's mean from the fixed effect. The 0.5617 represents the deviation at each time point from their average across the 3 time points. And right there is the fixed effect. That is saying that on average across all people, across all time points, we average 0.922 drinks a week. Lovely! So that is a random effects ANOVA. Again, random effects ANOVA has no predictors. Let's go ahead and look at a random intercepts model. So with a random intercepts model, we now add a predictor. And if we have a random intercept, we allow the intercepts to vary, but the slopes are fixed. And again, notationally, this is what it looks like. B0j is equal to B1 times age 14 plus EIJ. If you were to expand the B0j, by the way, we call that the level 2 model. So if we were to expand the level 2 model, we would say B0j is equal to gamma 00 plus U0j. So again, the intercepts are allowed to vary, but the slope is fixed. And if we were to put it all together, this is what it would look like. Yay, hallelujah, wahoo. And then if we were to look at it in R, this is what the equation would look like. Again, that age 14 tells R that there is a fixed effect because it is outside the parentheses, and then within the parentheses we have a 1 that tells R that the intercepts are allowed to vary across IDs. And if we were to use just summary of rand.intercept, we would get something that looks like this. And again, we have an estimate of the variability of each group from the fixed mean, 0.5966. And then we have an estimate of how much each individual differs from their average effect across the time points, and that's 0.4915. And then now, instead of having one fixed effect, which was the slope, we have 2 fixed effects. We have a 0.65 for the intercept and then 0.27 with the slope. So what is this telling us? This is telling us that on average, at the age of 14, because remember an intercept is whatever your 0 point is. Remember there was a column that had 0, 1, and 2 represent 14, 15, 16. And that's one of the reasons, just so the intercept is easier to interpret. So this 0.65 tells us this is the average number of drinks across all people, across all clusters, at the age of 14 years old. So on average, people who are 14 in this sample, they average 0.65 drinks. And the 0.27 means that every year they got older, they increased the number of drinks they had by an average of 0.27. Nice and lovely. And of course we could visualize this using FlexPlot. And we get a graphic that looks like this. Again, we have a solid black line, which represents the fixed effect. And then we have the different colors representing the slope for each and every individual. So let's go ahead and do a random slopes model now, which means we're gonna fix the intercept. And again, you normally wouldn't do this, but just so you can know how to do it, here's how you do it. So here's what our equation looks like. Now we don't have B0j because we're saying that the intercept is fixed, but instead we have B1j. And B1j, if you were to expand it out, the level 2 model becomes gamma 10 plus U1j, or we have a fixed slope, which is gamma 10, and then a deviation from that. And if we were to put that all together, we would just replace B1J with gamma 1, 0 plus U1J. And if we were to look at this in R, what would it look like? Again, we have age 14 corresponding to the fixed effect, so we are telling R that age 14 has a fixed effect. But again, within the parentheses, we have a -1, which is the way that we tell R that the slope should not be random. And we also have age 14 that is random. Age 14 here corresponds to gamma 1, 0, and then age 14 here represents this parameter, which basically says that every individual is allowed to have their own slope. Lovely, lovely, lovely. And if we were to do a summary of this, we would see now that we don't have any variability about the intercept, again, because the intercept is fixed, but now we have variability about the slope. And so that 0.225 basically says that people's slopes differ, and the degree to which it differs is represented by the variance, which is 0.225. And if we were to visualize this, we would see something that looks like this. Again, we are fixing the intercept to be the same. It's kind of weird, but we can do it. And we see that the slopes are varying. And of course, we naturally want to do a random slopes and intercepts model. And so now we have B0J and B1J. And if we were to look at the level 2 models of each of these, we would have a gamma 0, 0 for the intercept and a gamma 1, 0 for the slope. And if we were to put it all together, this is what it would look like. Hooray! These terms right here represent the parameters for the intercept, and these right here represent the parameters for the slope. And to do it in R, this is what it would look like. Again, everything outside of the parentheses is a fixed effect, so we have a fixed slope and a fixed intercept. And within the parentheses, we have a random slope. Now, we don't have a 1 in there. And the reason why is because in R, you don't have to specify a 1. And the reason why is because if you add a predictor in R, it assumes that the intercept is also random. So you have to explicitly tell it -1 if you don't want it. If you do want it, it's going to implicitly be there if you have any sort of predictors in the model. So now we can, again, look at the variability about the intercept. Right there, 0.6355 represents the degree to which individuals vary in the amount of alcohol they consume when they are 14 years old, because again, when they're 14 years old, that is the intercept value, or that is the value at which the slope is equal to 0. And then the 0.1552, age 14, represents the degree to which these young individuals vary in the degree to which they increase in their alcohol consumption as they age. And by the way, it might be helpful to look at the two outputs side by side. So on the left, we have a model that has just a random intercept and a fixed slope. And on the right, we have random slopes and random intercepts. And you'll notice the difference in the residual error, or sigma. So when you do not allow the slopes to vary, you have a larger residual. And that makes sense. If you're forcing everybody to have the exact same slope, your predictions are going to be poor. They're not going to be as close to the individual dots. On the other hand, in this one, we have a much smaller residual error, and that again is because each individual is allowed to have their own fit. And here is what it would look like if we were to visualize it, and that looks all pretty and stuff. Again, the black line represents the fixed effects, and then the color lines are the random effects for 3 randomly selected individuals. So let me summarize for you, because that was complicated. I understand that, and I'm sorry it's complicated, but it kind of has to be complicated. Remember, fixed effects means that that effect is applied to every individual regardless of cluster. We might call it a common slope and a common intercept. And by the way, I don't know if this was clear, but every time you model a random effect, there is also going to be a fixed effect. So each individual cluster might have a different slope, but there's always going to be an average slope across all clusters. And that's what we call the fixed effect. And then we have random effects. And you include a random effect when you expect that within the clusters they might deviate from the average slope or intercept. So do you expect each cluster to have their own slope? Add a random effect. Do you expect your clusters to have different intercepts? Add a random effect. And like I've said before, typically we don't add a random effect for categorical variables, though you could. So with that, let's review our learning objectives. Number 1, understand subscript notation in regression. Again, we use an I to indicate which row we are at in the dataset. Number 2, understand subscript notation for mixed models. So now rather than having just an I, we also have a J. The I represents the individual, the J represents the cluster. Number 3, understand the following. Random effects ANOVA. Again, that means you don't have any predictors. You're just modeling the differences in the means. Random intercept model. So the intercepts are allowed to vary, but the slopes are fixed. Random slopes model. So again, that means they originate at the same point, which is kind of wonky, but their slopes are allowed to vary. And of course, understand a random slopes and intercept model, where both the slopes and the intercepts are allowed to vary. Next, understand what fixed and random effects mean. Fixed effect means that every individual in the sample gets that value in their equation, and it is represented again by that solid black line. So when determining everybody's score, that line is added to their score. Number 4, understand what gamma 0, 0 and gamma 1, 0 mean. Again, gamma 0, 0 is the fixed intercept and gamma 1, 0 is the fixed slope. Also, have a basic understanding of how to do a random effects ANOVA in R, how to do a random intercepts model in R, how to do a random slopes model, and how to do a random slopes and intercepts model. And finally, have a basic understanding of visualizing these models in R. And I say now a basic understanding because we're going to revisit that in the next video. Until then, peace out.